Welcome everyone to this week's edition of the HoloTube seminar. We are very pleased and happy to have Julian Sonner tell us about causal symmetry breaking. And Julian, the floor is yours.
Okay, thank you. Thanks for everyone. Thanks to everyone for being here. Thanks for the invitation. Very happy to contribute to the seminar series. I've appreciated quite a few of the talks, although on YouTube, not in person. But the talk that I'm giving today, I think, is maybe a little bit different from what is usually the focus, although there are plenty of connections. And basically, what I want to talk about is really strongly related to black hole physics, but the approach that I'm taking is going to be related to quantum chaos. So, so what is causal symmetry breaking? In some sense, that's the point of this talk, to explain to you what it is and why it's useful. But before, I want to say a couple of words also about all these wonderful collaborators here. So I'm mostly talking about 3 papers, only 2 of which have appeared. So roughly speaking, also thematically, I'm going to talk about properties of the spectrum of holographic theories. And this is work with Alexander Altland, who is in Cologne. Then I'm going to talk about adding also operators, so talking also about properties of operators in holographic theories. That's some ongoing work, but that should appear pretty shortly. With Alex again, with my postdoc Pranjal Nayak and my PhD student Manuel Bielma. And finally, specifically about properties of Ope coefficients. That is some work, part of which is published with Alex Belin and with Jan de Boer, and again with Pranjal. And there's another one forthcoming. But also chronologically, the talk, I will first talk about only the spectrum, then I will add the operators, and if I have time, I will talk also about Ope coefficients. So, however, let's talk about more physics. Let's talk about what is the motivation, what is the general context. So, as no doubt all of you know, quantum mechanical unitarity and gravitational physics have long had a fraught relationship. So there seems to be something that doesn't sit easy. Either one or the other seems to be in tension with the results that we get from our theories. So most famously, this is illustrated by what's known as the black hole information problem. And in particular, here I want to think about its ramification for what's called the page curve. So whether it behaves like it is expected to in a unitary system or it does not. But also, in some sense, perhaps more down to earth, one can find these signatures of a tension between unitarity and what the predictions of semi-classical gravity, to be specific, are in the long-time behavior of observables. For example, such things as simple observables like two-point functions. And in a nutshell, these kind of paradoxes arise precisely when we take seriously the results of Bekenstein and Hawking, namely that black holes are thermodynamic entities. So if we want to understand them as thermodynamic entities, they seem to have peculiar features that they don't share with other thermodynamic entities, but we would like to reconcile them. We would like to be able to treat them just as normal thermodynamic entities. And this is the whole, let's say, battlefield between unitarity and semi-classical gravity. Now, the strategy that I'm adopting is one, well, that I have been adopting for some time now. Basically, if we want to understand this paradox regarding thermodynamic black holes, or the thermodynamics of black holes, a nice idea is to study actually how do these systems arise. So how do thermal states actually arise as a dynamical process in quantum gravity? And of course, all our favorite arena for quantum gravity, I think, is ADS via the ADS-CFT correspondence. So I want to focus my attention on the issue of black hole formation and evaporation in ADS and within ADS-CFT. So this cartoon that I have here, it's actually from an older paper with Tom Hartman, Tarek Anous, and Antonin Rovai, for a series of papers with combinations of these authors, where we demonstrated specifically that you can actually set up our field theory in a non-equilibrium initial state that will have a non-trivial time dependence that in the bulk precisely corresponds to the formation of a horizon and a singularity that is a black hole and its subsequent evolution. And what turns out to be sort of the right framework to address these questions is that of thermalization, and thermalization at all timescales. So this can be early timescales, intermediate and late timescales. And what today's talk will focus on mostly is actually very late stages where we find ergodic behavior, and this ergodic behavior is strongly linked to quantum chaotic properties of the systems that are involved. So all of these things, I will put more meat on them. I will tell you what systems, of course. I will tell you also what is my working definition of quantum chaos and quantum ergodicity and so on. But the idea is we're going to hit our boundary theory very hard, and we're going to see what happens as a function of time, both on the boundary, and we want to make some statements about what are the bulk ramifications of these dynamics. Now, actually, just returning to these two examples, I mean the page curve and the correlation functions. In my opinion, both of these have recently enjoyed really spectacular new progress, but this progress, as so often, also came with new kinds of puzzles, or more positively, more positively, fascinating questions. And one of the most intriguing and important ones, to my mind, again, is the role of the ensemble. So this is a completely new thing that has come up, at least in this guise, and namely that it turns out that actually our holographic description of this process unearths solutions, so-called wormholes, which strongly suggests that there is actually something strange going on, namely that we average over an ensemble of quantum systems rather than stay within the usual framework of just having one quantum system. So let me just say a couple more words what I mean by that. So typically, of course, in ADS-CFT, what we say is we have one boundary theory, for example, n equals to 4 super Young mass. We have one bulk theory, type 2B strings in ADS. However, as I will argue rather carefully later, in such a context, it's at least unnatural to have these wormhole contributions, and I will be very specific why. However, these wormhole contributions are there, so we need to somehow understand how to interpret them. And to my mind, basically there are two attitudes. One, which is an attitude that has been proposed more recently in lower dimensions in particular, that this ensemble is just a fundamental property of ADS-CFT. So rather than this canonical view that I just explained, one bulk theory, one boundary theory, we actually have one bulk theory, but this is dual to a whole ensemble of boundary theories. Okay, that's on the face of it very strange, very different from what we usually say and think. Secondly, the ensemble can be emergent itself, and that is to say, this will be in fact the focus of my talk, that if you take very seriously the quantum chaotic properties of our boundary theories, you find that certain observables, in particular the ones which are dual to wormholes, are naturally described by an emergent ensemble. So the ensemble is basically let's say, something that very well approximates the true story, but the actual true story is still an individual theory. But the way that an individual theory can produce results that are equivalent to that of an ensemble, that's why I'm saying it's emergent. This will depend on the kind of quantities that we look at, and it will also depend on the kind of timescales that we look at. And this is what I would like to explain. This leads me to quantum chaos. So much for the background. I wanted to here is basically an advertisement of the results. So the slogan that I have chosen for this is basically from Dumas, one for all for one. The reason being that one theory can look like a whole ensemble of theories, and a whole ensemble of theories can be associated with one particular theory. And so this is the idea of the emergent ensemble. And the way that this works technically is precisely this route that we call causal symmetry breaking. So we use a simple symmetry breaking principle that applies to a broad class of quantum chaotic systems. And this symmetry breaking like any symmetry breaking, allows us to basically identify a set of relevant, very light modes, which we use to construct an effective field theory. And this effective field theory is the one that allows us to characterize precisely those quantities which are given by ensemble-like answers.
Did we lose Julian? Or is it me?
No, it's not you.
Okay, we can wait for a few seconds. Hopefully he comes back. Okay. He disconnected completely. That is progress, I guess.
I think you need some elevator music to play when this stuff happens.
Well, this is a first. So are there any questions that you want to discuss for now? So while we're doing this, I'll repost the slides in case you want to read through the talk so far. Okay, there's a okay, now there should be a link to the slides that you can access. I will pause the recording for now. Recording.
Okay, excellent. Let me just before we see this, okay, I'm the right network. Okay, so so we have these light degrees of freedom, which are basically determined by some symmetry breaking principle that I would like to explain to you. And we're going to use it as a conceptual tool and then also as a technical tool. I think this is where I cut out. So unlike my internet, this will be a very efficient tool, and we're going to use it to make some new specific quantitative predictions. And depending on time, I might talk about one of several aspects there. So let me talk about this effective field theory of quantum chaos, and let me try and connect it in particular to holography, because this is our all shared interest. So quantum chaotic models. So the idea actually is that we look at the spectrum now of what is a quantum chaotic model. And in some sense, the definition of a quantum chaotic model is that if you look at its distributions of energy levels, the distribution of energy levels is given by particular mathematical functions that have been conjectured by Wigner a long time ago. So the idea is the following. Let's look at this plot in the top left. So this is S is a measure of energy. In particular, it's a measure of energy difference. So we could actually think of this as delta E, delta energy. And what we do is we fix one level, energy level of a quantum system. One might, to be concrete, take this famous example of Sinai billiards, but that's just a very simple quantum chaotic model. And you put yourself onto one energy level and you ask, how likely is it that if I go away in energy from that one level that I encounter a second energy level? And the way to do this is, well, one fixes oneself a little window of energies and one bins the number of energy levels that one encounters. So if I make a histogram, okay? This gray line here is really a histogram of the number of levels at a certain distance from my original level. And the idea is that for one single quantum system, if I do this histogram well, then I compare it to a prediction of Wigner. It is very well approximated by this Vignette prediction. So what is this Vignette prediction? This Vignette prediction actually says you take at random the Hamiltonian. You at random sample the Hamiltonian from a particular distribution, and then you average with a particular probability measure over all such possible random choices. And that gives you a continuum curve. This is the purple curve. And the idea is, as I said, that the individual quantum system approximates very well, or is very well approximated by this ensemble here. That's really, in a nutshell, all there is to say. So the point is that if you take the limit where there's many, many energy levels, and then you correspondingly are able to make the bin size smaller and smaller, you're supposed to get a better and better approximation. So this is, in some sense, a very physical way in which one single system approximates an ensemble average. So I repeat again, this is the distribution of energy spacings in a given quantum system, but I sample it over the entire spectrum, and I have to do some sort of binning. And the result that you get is arbitrarily well approximated by an extremely smart guess by Wigner. Namely, he guessed that you get energy levels that are distributed as if you drew randomly a Hamiltonian from a probability density, and then you average over that probability density. And this causal symmetry breaking that I'm going to tell you will explain to you how that works. Okay. But Wigner guessed this in the 1930s, I guess, and then this became a whole field, basically random matrix theory. In particular, in nuclear physics, this was first developed in nuclear physics by people also like Dyson, by Mehta, and so on. Now, a related quantity, which is basically the same quantity, but that you maybe have seen more recently in the context of black hole physics, is what people like to call the spectral form factor. And this is easily explained now because it's just the Fourier transform of this curve. So if I Fourier transform this curve, or a closely related one, which is the two-level correlation function, then I get a time domain picture. In this time domain picture, it has something that behaves exactly like the ensemble. I'm calling the ensemble here RMT, random matrix theory. So the purple curve has the same meaning. This is the prediction, let's say, of Wigner if you Fourier transform. And then you can ask, what does a real individual system look like? And the point is that after a certain time scale, I will explain why, after a certain time scale, it is arbitrarily close to this prediction. What happens before that time scale is more complicated, is not universal, or is less universal, but that shall not concern us right now. But the point is there is a time domain imprint on interesting quantities, and then there is an energy domain imprint. And the idea is that an individual quantum system can be arbitrarily well approximated by a random system, an average over an ensemble of systems. Okay, so this is, and by the way, one can also say this is a definition of quantum chaos. A quantum chaotic system is one whose energy statistics coincides with the predictions of random matrix theory. All right, so now the idea of causal symmetry breaking in a nutshell is the following. So we want to say something in the first instance about the level spacing statistics. So we better talk about the density of energy levels, rho of E. And as you know from your basic many-body physics or quantum field theory, the rho of E can be seen as a discontinuity of the advanced correlation function across the real axis. So G advanced minus G retarded evaluated at E. So this is some I epsilon prescription, of course. And so the imaginary part, if you want, of the advanced correlation function, or minus the imaginary part of the retarded correlation function, gives you the spectral density. This is just a textbook definition. But this means, of course, that if you have a non-zero spectral density, if this thing is supposed to be zero, and technically speaking along a finite interval, so a branch cut, then G plus of E must be different from G minus of E, right? Otherwise, this would be zero. So the key idea is that we can actually understand the difference between the prediction of the retarded correlator and the advanced correlator along this cut as a spontaneous symmetry breaking. So I will write down for you a theory which has as a saddle point the solutions for G plus and G minus, such that G plus along the cut will be different from G minus along the cut. I will, of course, have to explain to you what this mean field is and what this effective theory is, but this is the idea. So if the advanced causal sector and the retarded causal sector were entirely equivalent, this is what we call causal symmetry, then the spectral density would have to be 0. Let me add 1 point because sometimes I get questions. When I say 0, I mean 0 almost everywhere, which means I do allow poles, but not branch cuts. However, therefore, necessarily, if it is non-zero along a finite support in an interval, then these two sectors must be inequivalent and this causal symmetry must be broken. Now, here I've already introduced this average. I've actually told you already what this average is. This is not an average in the sense of averaging over Hamiltonians. It's much simpler. It just means, for example, take a little energy window and you sample the number of energy levels within the window. So this is just the same sense as I've made a histogram here. You see that the histogram here, that does imply a little bit of energy coarse-graining because I'm lumping all the levels that are within this interval, I'm lumping it into the same bin. Okay, so some kind of this average has to be done for this effective field theory to be stabilized. So you can do it with respect to the eigenstate ensemble, which I just explained. This is just the binning, but you could also think about just averaging over a small set of parameters, like in n equals to 4, for example. You could imagine averaging over the 't Hooft coupling or some other marginal parameter, or maybe someone can come up with another suitable coarse-graining. Right, so now let's do it. Let's get more into the meat of this. So the point of the departure is actually a ratio of determinants. Why a ratio of determinants? Well, the idea is that this gives you precisely a generating functional to calculate imaginary parts of causal correlation functions. Why is that? Well, let's just look at it. If I take the derivative with respect to Z1, for example, Z1 is like an energy, right? It's like energy 1 minus the Hamiltonian. This is some functional determinant. Well, I'm just going to get the determinant back times trace 1 over Z1 minus H as an operator. Okay, so trace over 1 minus Z1 minus H is precisely the trace over the G plus or the G minus correlation function. It depends on which side of the imaginary axis I am, right? Trace over 1 over Z minus H is the trace over the propagator. In the, in a certain community, this is also known, of course, as the spectral resolvent. But okay, for us, it's just the imaginary part of the Green's function. And so why do I have ratios of determinants? Well, because at the end, I have to normalize the correlation function. So what I do is I take derivatives with respect to Z1 and Z2, for example, and at the end, I set Z1 is equal to Z3, Z2 is equal to Z4, and then the determinants cancel, and I'm just left with my correlation function. So the determinants in the denominator and the numerator are just in order to cancel, to normalize the quantity. Let me just remark that this is very similar to what people would usually call a replica trick, but I think it's a little bit more elegant because you only need a finite number of determinants and you don't need to do analytic continuation in the number of determinants and so on. And in particular, it's also elegant because it says something very familiar to high energy physicists. This basically introduces a supersymmetry because remember, determinants in the numerator are given by fermionic path integrals and determinants in the denominator are given by bosonic path integrals. And I can make that explicit by doing a trivial rewriting of this. I can basically write the determinant of Z1 minus H as a path integral over a set of fermions, with the kernel being just Z1 minus the Hamiltonian, okay? So what I need is I need to introduce fermions for this determinant, fermions for this determinant, bosons for this determinant, and bosons for this determinant. In other words, I need to introduce a superfield, a supervector. And to be specific, if the dimension of the Hilbert space is L, then in order to exponentiate this ratio of determinants, I need a 2L/2L supervector, where L is the dimension of the Hilbert space. And so I'm writing a path integral that just gives me this ratio of determinants. Now, what's interesting is that this automatically has an interesting symmetry. And that's because the Hamiltonian in all of these four determinants is the same. So if I rotate from one Hamiltonian to the other, I should have a symmetry. And so each of these sectors can be rotated in the other sector. And that gives me a continuous U2/2 rotational symmetry. Of course, just for the astute reader, basically, this is weakly broken explicitly already by the fact that I've made the energies in the different sectors to be different. But that will be very useful because a weakly explicitly broken symmetry is precisely the kind of thing that lends itself well to an effective field theory treatment. Let me just say pions. Okay, so this will actually be very similar to the way that we build effective theories for pions, where you have chiral symmetry, except it's explicitly broken by the masses of the quarks, small masses of the quarks. So we should think of these energy difference like the masses of the quarks. But in addition to this small explicit breaking, you will see that the mean field of this theory will break the U2/2 spontaneously. And the most simple pattern that one can kind of come up with is this one. U2/2 is broken to U1/1 times U1/1. So the individual rotations between two of these pairs of determinants still remain, but the overall symmetry is broken. So this is going to be by saddle points, and the effective theory that results from it is going to be stabilized by a large Hilbert space dimension. So this theory is going to be very good if the number of degrees of freedom is large, and it's also going to be very good if this breaking in energy differences is small. And both of these are precisely the regime that we want to be in to describe our holographic applications. Right, so there is a symmetry between Z1 and Z2. I don't want to go too much into it now, but people like to call it the Weil symmetry for actually mathematically well-defined reasons. Now, what happens is now that there are these Goldstone modes that are related to the symmetry breaking, and we use them to build our effective field theory. And let me just give you the preview. The resulting model reproduces precisely the physical content of random matrix theory. So, right, if I only focus on the light modes, I get precisely random matrix theory. But as you can already maybe put together in your heads, you have all these other modes that maybe dominate at other timescales, and they show you deviations from random matrix theory. But to the extent that the effective field theory is a very good description of my system, to the same extent, the ensemble is a very good description of my individual system. So that's, I think, a very nice point of view. Moreover, there's a nice geometric picture behind it, as was demonstrated to us in a very general sense already by Callan, Coleman, Wess, and Zumino. So the way that you write, of course, the effective field theory is you use coset description of the nonlinear realization of the symmetry. So we're going to write basically an integral over the coset. So Q is some degree of freedom that parameterizes this coset, and the coset follows from the symmetry breaking principle. So I remind you that we had this U2/2 was broken to U1/1 times U1/1. So the coset is going to be U2/2 divided by U1/1 times U1/1, and that will be the target space of my nonlinear sigma model. So again, let me be clear here with the comparison with the pion effective field theory within QCD is actually very useful and is a very close comparison. So we introduced these auxiliary degrees of freedom, which are graded. So these are, super vectors, super fields. You might call them fermions and bosons. In QCD, we have our actual quarks. So the symmetry is broken by a quark condensate, the chiral condensate. This breaks the chiral symmetry. Our causal symmetry is broken by a condensate of these psi fields. Remember, I introduced them here to exponentiate these determinants. They were purely auxiliary quantities from this point of view, but we're now going to take their field theory seriously. Not because I want to ascribe them some physical reality. That actually, just as to preview, I can do if I look at the bulk picture, but here, just because it's useful. So these degrees of freedom will allow me to explicitly realize the symmetry breaking. And then the chiral condensate, you also have a quark mass, which explicitly broke the symmetry, but by a small amount. And here we have the energy differences, which actually break this symmetry also explicitly by a small amount. And in fact, the amount typically that we want to break the symmetry is going to be non-perturbatively small in the entropy of the system. I think I will explain why in a later slide. Okay, so is this so far okay, or are there questions? Also maybe about the introduction, because actually, sorry, we were somewhat rudely interrupted by my internet problems. Okay, looks fine. So now the key point is that a saddle point analysis of this path integral is justified by the large dimension of the Hilbert space. So I'm looking at a quantum system that has a large Hilbert space. Then I'm allowed to do this integral here by saddle point. There are a few steps in between that you need to use to argue this, but it is true. So then I try to do this path integral by saddle point, and I find immediately in this particular example where the coset manifold is this U2/2 divided by 1/1, 1/1, I find immediately a saddle point and a Goldstone manifold, which is of the form hyperbolic two space times a two sphere. And the saddle point that I find, that the most obvious one that people like to call the standard saddle, you can put it at the north pole of the sphere. It's just a choice of coordinates. But because there was this exchange symmetry between two energies, I called it the Weil symmetry, you can actually immediately generate from the standard saddle point, you can generate a second non-standard saddle point, which is at the south pole in this parametrization. And in the quantum chaos community, this saddle point is actually known for a long time. It's known as the Andreev-Altshuler saddle point. What's interesting and important is that this standard saddle point, just in the way that we refer to it, it has the property that it completely leaves intact the supersymmetry. And if something is supersymmetric, then you can show that its action here has to vanish, because the action will be always written in terms of supertraces, and the supertraces of something that's fully supersymmetric is always 0. But the Andreev-Altshuler action actually breaks the supersymmetry. Okay, so we have two saddle points. Both of them break the causal symmetry that was by design, but only one of them breaks in addition also the supersymmetry. That's the Andreev-Altshuler saddle. Now, why have the saddle point, I can of course perturbatively expand around one or the other of these saddles. And the perturbative parameter is the energy difference divided by this quantity delta, which is the mean difference between two energy between two energy levels. So here I can now let me pause a little bit and explain that, because I haven't explained this before. First of all, there is a typographical explanation. There is capital S, which is entropy, and there's little s, which is energy. Unfortunately, this is standard in the literature. So little s, energy difference divided by the mean level spacing. So now if I have a Hilbert space, which has approximately e to the entropy number of states, right? Our Hilbert space has e to the entropy number of states. Then the mean difference between two states will actually be 1 over the number of states. So it will be e to the minus entropy. So the spacing, the average spacing between two energy levels is non-perturbatively small in entropy. And this variable little s is energy measured in time in units of the mean level spacing. So it is a non-perturbatively small quantity if I think about it in terms of entropy, right? So this is e to the minus entropy to some power n. However, this is the natural expansion parameter around both of these saddle points. So this theory, just to say, is intrinsically non-perturbative. This is very different to essentially all the other approaches that have appeared in the literature and have been dealing with these wormholes. Our approach is intrinsically non-perturbative. And what's even more even more powerful in some senses, that the second saddle, it's actually what people like to call doubly non-perturbative. Why is it? Because its action itself is of the order e to the entropy. But how does a saddle contribute? Of course, it contributes in the exponential. So the size of contribution of the second saddle is actually e to the entropy. This is what people like to call doubly non-perturbative, and is this kind of effects that people have been chasing a lot using a microscopic approach. In our field theory, this is actually relatively easy to achieve, right? So the non-perturbative expansion is just very easy. It's the standard expansion about these saddles. But if I add the contributions of the two saddles, in addition, I have a doubly non-perturbatively good resolution. Okay, so that's actually very powerful, and this is what makes this effective field theory so interesting. Good. And what should the other thing that I should say is that the fact that the mean level spacing is like non-perturbatively small also tells us that the effective field theory is actually very good, because we said that the effective field theory is going to be good if the energy separation is small. The energy separation I just explained to you is naturally very small in precisely the regime that we want to investigate. So this is the comment here. Nice. Okay, good. So then now let's do something with this theory. So we can basically write a perturbative expansion of this theory, and the perturbative expansion of this theory it can be again written in terms of a matrix valued field. Why is it a matrix valued field? Because basically it parameterizes this coset. But it's just, in the simplest case that I'm telling you about, it's just a 4x4 matrix. Yeah, it's a U2/2 matrix basically. So it has 2 fermionic and 2 bosonic directions. It's a small matrix. And why am I sort of going on about the fact that it's a small matrix? Well, because the Hamiltonian itself, if you think of it as a matrix, it's huge. So if you wanted to apply directly a sort of a microscopic approach to the Hamiltonian itself, you would be talking about a matrix of an enormous size, whereas here we just have an order 1 size matrix. But nevertheless, you can still do a usual matrix field theory expansion, and the matrix field theory expansion can be organized in topologies. And I've done this for you here, so I can actually classify this matrix field theory in terms of Riemann surfaces. For this quantity, I'm now asking about the level spacing distribution. This is precisely the quantity that I introduced in the beginning. I'm going to get Riemann surfaces with 2 boundaries. Each boundary is going to be associated with 1 energy level. So I have 1 energy level. I told you I fix 1, and I ask how likely am I to find a second energy level. Each energy that is fixed is going to give me 1 boundary. So I'm getting 2 boundary Riemann surfaces of arbitrary topology that contribute around the standard saddle, and I'm getting the same around the Andreev-Altshuler saddle, only that the geometries are slightly different. This is this torus prime, torus with a hole prime, torus with many holes prime. But what is great is that we were able to match each of these 1-to-1 to one of these predictions that came from the gravitational theory, in this case, JT gravity. So the idea is that the Sanford group has basically calculated these terms that give you answers about level spacing distributions from a bulk perspective. And they showed that the bulk itself can be equivalently rewritten as a matrix model. And we were able to map our effective field theory to certain terms in the matrix model. And the way that we did it is we mapped the topologies. Right, so this is, in other words, the following, let's pause for a second and make the following determination. So the idea is that this lower dimensional gravity is supposed to be equal exactly to an ensemble of random matrices, right? This was this duality between JT and the matrix model. What we have shown here is that you don't need an ensemble of matrices. You can pick out all these contributions just by applying our effective field theory to a single realization of that of the quantum chaotic theory. So for example, the SYK model, if you want. Now, how am I doing for time? Okay, right. So I want to talk a little bit about applications, but I realize also that I've actually covered quite a lot in terms of conceptual points and in terms of technical points. So again, maybe it's a good time to ask if there are questions about this.
I have a question, actually.
Yes.
Is this equivalent to the statement that the model is self-averaging?
That's a very good question. It's not equivalent, and how should I say? But this is actually a key question to ask. So here, maybe with this graph, I can answer it. So what this effective field theory computes for you is basically the purple line here. Okay, but now you should ask, or you have asked, what is actually the meaning of the purple line for an individual theory? So let's say we take n equals to 4. Well, actually, n equals to 4, the actual curve would look more like this. So you would find the early time behavior would be as drawn, but as you start approaching this EFT prediction, you actually get erratic fluctuations, and only if you average over the fluctuations do you get a continuous curve. So what's the averaging? Well, it could be a small energy averaging like I did in the introduction, or you could do some continuous time averaging. So you keep tracking the time series and you average it over small time intervals as you go on. And if you do that to the individual theory, then you get precisely the prediction of this effective field theory. So the effective field theory gives you, if you want, an envelope function for the actual individual theory. Right? So there is a meaning to the curve in the individual theory, but it's not that it literally behaves at any instant in time like the theory. So if you want, it gives you the mean, but there's also a variance that is non-zero. And you might also want to compute the variance, for example, of this curve. And you might want to compute higher moments of this curve. Okay?
Yes, okay, I understand that. But actually, since you've mentioned like higher moments, because here, like the expression that you had is just a relation between two energy levels, right? And like one can look into the correlation of like more energy levels. Is there any meaning in that? Like, or can it be achieved with your model?
Absolutely. So I would have said that I strongly believe that it can be done, but actually one of my friends and also collaborators on other projects told me that he has recently been able to achieve this. So I won't spill the beans yet, but yes, it's possible. Yeah, and it's this the conceptual technical framework is actually the same.
Okay, thank you.
Sure. Other questions? Okay, so then let me go to applications. So I'm just trying to see what would be. Yeah, let me just proceed. So here, this is again giving you a little bit more detail about what this curve actually means. So as I explained at the time, this Z4 is a generator of the spectral resolvent. So you can actually get several spectral resolvent correlations. And given the discussion that we just had, I've only given you the formalism to get 2 resolvent correlations, but you could go to 3, 4, 6 resolvent correlations. So now what I wanted to say is that this allows us, this 2 resolvent correlation allows us to evaluate precisely the 2-level correlation of functions using the EFT. And in fact, the leading contribution to this comes from a single diagram. So technically speaking, it comes from a cross correlation between 2 super traces, where this one, red, you should think of as being the retarded sector, and blue you should think of as the advanced sector. But the interesting thing is that this is fully predictive. So I can actually do this contraction here can tell you what does it contribute to the two-level correlation function. And if I normalize by the mean level spacing, so I use this S variable that I introduced earlier, the coefficient is exactly -1/2. This is totally a prediction. The coefficient is a prediction. And you can ask, is this prediction actually borne out in holographic theories? So that will be the next slide. But what I wanted to say is that, okay, it just comes from the standard saddle. So there will be a non-perturbative correction to this from the other saddle, but I'm not gonna go into those details here. But it also comes just from the simple propagator, the contraction between these B matrices, which is just a rewriting of the Q matrices that I had earlier. So the B's are just the degrees of freedom on the coset. But if you go and you Fourier transform it with this coefficient here into real time, you just get a linear in time rise or a twice linear in time rise. That depends on whether you have time reversal symmetry or not. So this coefficient 1 and this coefficient 2, again, is a pure prediction of this effective field theory. And so now we went to the literature and we said, is this borne out? So as I told you, topologically, this first diagram should be mapped to what people like to call bulk wormholes. So these come with different names. In this JT story that has been related to the Stanford Schenker matrix model, the SSS matrix model, they call this contribution the double trumpet. So each of the boundaries of the double trumpet correspond to one insertion of rho of E. So you have again a rho of E primed correlation function. And if you expand it in energy difference, then you get a regular part, which we don't care about. And you get a singular part, and the coefficient of the singular part, if you divide it by the level density of JT gravity, it's precisely -1/2. So, very good. The effective field theory precisely captures that universal coefficient. Well, there is an older story in some sense, which is called minimal string theory, in which case one also has a bulk picture. This is described actually in detail in the paper with Alex Altland. But the double trumpet gets translated to a different kind of diagram that you should compute. And this is known historically as the FZZT annulus diagram. So FZZT stands for Fateev, Samologikov, and Teschner. But it's basically the amplitude between two brane insertions. So each of these is a brane. The brane fixes the energy. This fixes one energy. The other brane fixes the other energy. And Emil Martinek was so kind to actually calculate this amplitude already in 2003. Again, we expanded it in energy difference. We get a regular part, which we don't care about. And we get precisely the -1/2 coefficient in the 1/s² diagram. So it also works. But perhaps more exciting, even in higher dimensions, these recent so-called 3D Taurus wormholes that are supposed to be the higher dimensional analogs of this double trumpet, they were proposed by Kotler and Jensen. Again, we expanded their result. You get regular part, and you get precisely the coefficient of -1/2. So we had already reasons, from fundamentally the theory, how it's set up, that this gives you the leading wormhole contribution in all of these theories. But it's nice to see that in each case where it should work, it also works. So the leading EFT diagram is dual to the contribution of the bulk wormhole with trivial topology. So you could also have non-trivial topologies, but I don't think I have time to get into it. But you probably can imagine that those have to do with these higher topology diagrams in our effective field theory as well. Now, okay, let me see. So maybe I do want to say a few words about this, because this is the most recent paper that we published. This takes a little bit of a detour, but I think it's very interesting. So for me, this actually explained and gave me some confidence that really these Euclidean bulk wormholes that people have been throwing around, really we should take them seriously. But the way that I am taking them seriously is that they give you universal contributions to the spectral correlations of our boundary field theories that are induced by the fact that they are chaotic systems. Okay, so these chaotic systems, they have certain universal features of their level statistics, and those universal features in the bulk are precisely captured by these wormhole geometries. So we should not actually be nervous that these wormhole geometries are there in the bulk. People, when they were first proposed actually by Mulder, Sen, and Maus, people were nervous because they didn't fit into a standard picture of ADS-CFT, right? In fact, we should be glad because they give us a way of computing the moments of the distribution of energy levels, okay? And the key ingredient is to realize that this comes from quantum chaotic dynamics. Okay, but now I have accepted that these bulk wormholes are there. So let's ask, what can we do with them? Okay, so this is in some sense the next step. This is this recent paper that I wrote with Alex Belin, Jan de Boer, and Pranjal Nayak. So what we could do is we could ask what other bulk solutions are there and what do they tell us? So what we were looking at is we were looking at the global charge. So for example, just simple electric charge of some operators. By the way, ETH here stands for eigenstate thermalization hypothesis. This is actually another very powerful framework that allows you to talk about the spectrum of quantum chaotic systems. I've focused a little bit more on the RMT aspect up till now. In this paper, we were focusing a little bit more on the ETH aspect, but actually you can understand it just from what I said previously. So the idea is that if you put yourself in 3 dimensions, so ADS3, there is a solution that was written down by Mulder, Sen, and Maus, which is called the Genus Two Wormholes. So you take a Genus Two Riemann surface on the boundary, 2 holes, and then there is a connected bulk solution which has 2 asymptotic boundaries, each of which is this Genus Two surface. And now I can ask, what happens if I insert a charged operator on each of these boundaries and I ask about its 2-point function? Well, because this 2-point function is actually not neutral under the symmetry, but the 1-point function of these operators should be 0 because it's a charged operator. It carries a non-zero charge under an exact symmetry of the theory. So it has to have a 1-point function. But this is a very strong statement because its 2-point function has to be exactly 0. It's not that it has to be somehow approximately 0. It's exactly 0. So it also can't have any higher moments. Going back to the discussion that we had before. If a signal is just always 0, it doesn't have any standard deviation and it doesn't have any higher moments. But the existence of this bulk wormhole actually predicts that there is a non-vanishing variance of this operator. And that's very disturbing because we just said that's incompatible with our statement that there is an exact symmetry. Well, actually, the story is a little bit more interesting because you can show that if the symmetry in the boundary corresponds to a gauged symmetry in the bulk, then everything is fine. Because if there is a bulk symmetry in the bulk gauged symmetry, then you actually have to have a Wilson line that goes between these 2 operators, and you can actually use some very simple arguments, essentially a Gauss's theorem, that in fact, the correlation function is non-zero, even though this wormhole exists. So that's good. Sorry, the correlation function is 0. So we also have 0 variance. We have 0 expectation value, 0 variance, and 0 higher moments. Everything is fine. However, if the bulk symmetry is merely global, then you cannot argue that this correlation function generically vanishes. And in fact, generically, you would expect that it does not vanish. And that's very, very disturbing because it's completely in contradiction with our original symmetry-based statement that the 1-point function is exactly 0. And so the way that we point out that you get around this is that actually you must say that there can be no bulk global symmetries in a theory of quantum gravity. Otherwise you would get this paradox. So we can use these ideas of wormholes actually to give an independent argument for the absence of bulk global symmetries. It just comes from the existence of these wormholes. So this was the content of this paper that we wrote recently. And of course, there has been a long and very nice proof by Hallow and Oguri of this statement, but using sort of an algebraic quantum field theory approach, very different from our argument. Our argument is more like a physical paradox type argument. Okay, so let me not flash through all this other stuff that I have because it's just going to be annoying for you. So I think this is then the only application. So I had 2 applications. I basically told you about the spectrum, the spectral correlations, and how it is universally encoded by bulk wormholes. in accordance with the predictions of our EFT. And I've given you another exciting application, which is that if you add charge to the story, you can give a new argument why global bulk symmetries are not allowed in a theory of quantum gravity. So let me just go to my conclusions then. So we have said that we start by demonstrating that you can use a simple symmetry breaking principle to construct an effective field theory of quantum chaos. This tells us that you can get the same predictions as you would get from an ensemble just from chaotic dynamics. And this EFT is a precise realization of this idea. And I've also argued with you, I've only given you a couple of applications, but you can make a lot of calculations in a very simple way. And it's powerful, I did say that, because it's intrinsically non-perturbative. So the simplest expansion around the saddle is actually, from the microscopic perspective, non-perturbative. And even more, it has a second saddle, and the second saddle contributes things that are doubly non-perturbative, which are essentially infinitely hard to do from a microscopic approach. And this allows us I did not go into the details of how that works, but it basically gives us a way to control this rampant plateau physics analytically. So this is typically, because it's so non-perturbative, this is typically only under numerical control. We can do it analytically. And moreover, I think that it gives a simple geometric picture, and the geometric picture that emerges is that of the coset. So there is a simple geometric coset, and in fact, you can classify all the allowed cosets, and this actually coincides with the classification of all possible random matrix systems by collaborator Alex Altland and Martin Zirnbauer. It's a very famous paper now that's, I don't know, 25 years old or something. So good. So I showed you some applications. I did not show you the application to SYK. I did tell you about eigenvalue statistics. I did not even get to tell you about wave function statistics. So this allows you to talk about operators. But I expect that there are many more applications, and I hope to get back to you with those applications. Now, open questions. I think that will be nice to add. So the question that I got already went into this direction. The question is, can we add these erratic fluctuations in a controlled way? So is there some degree of universality to these? That I think is an interesting question. What generically is the bulk picture of causal symmetry and its breaking? So we have some we have some ingredients of this puzzle. I have shown you that the leading EFT diagram is wormholes. These other EFT diagrams are wormholes with interesting topology. What are the geometries around the second saddle? Well, generically, we don't have a picture. We have some level of understanding in minimal string theory. This is like a two-dimensional formulation of quantum gravity, basically based on Liouville and minimal models. Let me really not get into the details. If that interests you, that's in our paper. And of course, there is this wonderful work on JT gravity by the Stanford group, which also gives some of the ingredients. But it's very difficult to say in a very nice geometric picture from, metric picture, what is this Andreev Altshuler saddle? So we have some understanding in minimal strings. There is some speculation understanding in this JT paper, but I wouldn't say that either of these really have a very clear picture. But even more importantly, what is the generic description of it, like in higher dimensions? This is what I have put here as the big open question. What is the Andreev Altshuler saddle generally in the bulk? And in going there, of course, you want to also be a little bit more universal, how to associate bulk geometries to the diagrams of this EFT. So in 3 dimensions, this already works now, thanks to this Kotler and Jensen paper. And they also propose some high dimensional geometries. And I think some story can be made to work there. But again, all of this does not work around the Andreev Altshuler saddle so far, at least not in a conceptually clear way. All right. Thank you for your attention, and sorry for the technical hiccup.
No problem. We overcame the problems. So thank you, Julian, for a nice talk and inviting questions. I could start with a question if nobody else wants to. Then a very naive one that I asked myself from the beginning of your talk on, like, what do you refer to as an ensemble in this? Because we're used to like thermal ensemble averages, which we calculate as traces over density matrices and operators. So, but that's like, say, thermal averages, let's say within the canonical or grand canonical ensemble in the thermodynamic sense. But it seems to me like you're referring not to an ensemble of states, but you were referring to an ensemble of theories, right?
Correct. Good. So there, well, if you're familiar with the SYK system, that's a simple example of a system that is defined as an ensemble. But maybe the one that I was most referring to is random matrix theory itself. So the idea would be, so the original idea of Vignette would have been that if you take a very big nucleus that has a very complicated Hamiltonian, if you wanted to predict what are its energy levels, it is extremely difficult. I mean, analytically, no chance, and even numerically, I mean, back then anyway, it was impossible, but even today, numerically, very, very difficult. But so Vignette had this really genius idea. He said, actually, why don't we try the following? We know the dimension of the Hilbert space. So let us just sample at random a matrix of that dimension, which is Hermitian and maybe has some other symmetries, for example, time reversal. But that means that I need to specify a probability distribution for Hermitian matrices. So I give you some measure over Hermitian matrices. Nowadays, we can understand that, for example, in terms of just a potential. We can say this is, you have a potential for this matrix, like trace matrix squared, for example, or more complicated. But what Vignette was saying is that the actual level distribution of a real nucleus will be well approximated by calculating the level distribution of one of these matrices, but then averaging it over the measure. So you basically draw from an ensemble of Hamiltonians, but the observable that you calculate it not in the actual matrix that you sample, but you average over the distribution of all possible such matrices. And the point was that part of his genius insight was also that once you average, the problem becomes solvable, because the average prediction is actually analytically calculable. This is actually, and the answer for the two-level correlation function is precisely this curve here. Vignette already calculated it back then. It's called Vignet's surmise. And what is extremely amazing, in my opinion, is that he was right. That if you actually look at the energy spectra of complicated nuclei, they do approximate his prediction. Right?
So
So the ensemble means that you don't have one quantum theory, you have an ensemble, and there is a measure according to how likely is it to get an individual member of this ensemble. But then the quantities that you calculate quantum averages, and then you average them over a classical probability distribution.
So and
that's why this is not a quantum system, it's a family of quantum systems, and it's not, yeah.
And you're not labeling your states as before in, let's say, a thermodynamic ensemble by a fixed energy or other identifiers or observables, right? So you're labeling them by an average of Hamiltonians that have the same properties like symmetry, for example.
Yes, but I can still I can calculate whatever I want. I can calculate any expectation value I want of some operator. So that's just ordinary quantum mechanics if you want. But then after that, I take that quantity that I've calculated, maybe a correlation function, and I average it over all of the Hamiltonians that are allowed. And this second average, this is what I call the ensemble average, right? And that's the thing that, of course, we never thought would be the case in holography. We thought, you just have your Hamiltonian of n equals to 4, for example, and you have your bulk theory. There is no need to average over quantities. However, this average, maybe I can say this Now, so let's say you calculate the partition function of your Hamiltonian. If I calculate the partition function, that's just a number. It's the number that depends on the temperature, for example, beta. Let's say I calculate z of beta 1, z of beta 2. That should factorize because it's just the product of two numbers. You know, the partition function of n equals 4 at temperature 1 times partition function at temperature 2. And what's the bulk solution? Well, you know well what's the bulk solution. The bulk solution is just a product of two ADSs, but they're completely disconnected, just two ADSs. So you have a two boundary geometry, but you also have two bulks. Well, actually, however, if you do ADS CFT and someone tells you calculate all the bulk quantities that have two asymptotic boundaries, one with periodicity beta 1, the other with beta 2, actually, maybe now you're not that surprised, but there also exists a solution which is connected. It's just a two boundary bulk. But what does that mean? It means that z times beta 1 times z times beta 2 does not factorize, because it would factorize if the geometry itself factorized. And so the fact that ADS CFT gives you this non-factorizing bulk contribution very naturally, now you go, but how can you ever get that in a boundary theory? Well, you can't. You can only get it if you average over some kind of ensemble. So how you define this ensemble, okay, I actually gave you several ways of doing it. But a matrix model would be the simplest way of doing it. Okay.
Which I understand much better now. Thank you. Yeah.
And the whole point of my talk is that actually you can still reconcile this with just having one theory, but that one theory has certain contributions. Namely, if you do this histogram of energy levels, then the mean and the variance and all the other moments of that histogram will be described. And so the mean in particular is the two boundary wormhole. That's just, what does it give you? The quantity it gives you is the mean of the level spacing distribution of your one theory. That's the point in some sense that I'm making. Yeah, so thanks, it was a very clarifying question.
Thank you. I needed clarification. So any other questions?
Matthias, can I ask a question?
Of course.
Hello, Julian. Thanks
Hi.
for the nice talk. My question is somehow about the identification of wormholes in your effective field theory. I would like to understand, is it also possible to find the dual picture for traversable wormholes in your effective field theory construction?
Also a good question. And yes, I mean, there's much material. Maybe I should have been clear about this, but there are, of course, many different types of wormholes that are relevant in holography. The ones that are relevant for almost everything I said today are called Euclidean wormholes. These are saddle points of the Euclidean action. So the question of traversability doesn't arise. It's not a Lorentzian solution. So these are Euclidean wormholes, and there is no good Lorentzian story that I can tell you. However, there are also Lorentzian wormholes, and they also give interesting contributions, but they're not related to what I talked about today.
Ah, yes. Thank you.
Purely Euclidean saddles.
Yes. Thanks.
Mm-hmm. Sure.
Are there more questions?
Can I ask a question?
Certainly.
Hi, thank you for the nice talk.
Hi.
So my question is about what you had on your Outlook slide.
Yeah.
So on that slide, you were talking about the $1 million question, which is, what is this Andreev
1.2 million.
1.2 million. Yeah, right. In euros. Sure. So my question is the standard saddle well understood in the higher dimensional bulk spacetimes? No. So,
no, but there is a clear proposal. There's a clear
Okay.
proposal here, and that's these two boundary wormholes. And
Okay.
at least, for example, people like Kotler and Jensen have a proposal for how to construct them.
Okay. So I guess my question was, is there some way to employ all the tools from Resurgence to, if you know well enough what's happening in this perturbative expansion for the standard saddle, could you not extract that information you wanted for the non-standard saddle without having to go through some other trouble if it's too difficult?
Well, that's actually one of the things I would really like to do. It's, I mean, not a particularly active project, but it's a project that we're actually pursuing. However, so there is quite a lot of history to this. So for very simple quantum chaotic systems, those things are understood and actually go under the name of Riemann-Siegel lookalike. These are, papers in the orbit of Berry Keating, going very much into the pure math community. And there, I think people have actually done precisely what you said. Okay. It's some sort of resurgent way of getting it. Mm-hmm. Well, I guess my answer is basically just a restatement of your point. I find it very interesting. I'm not entirely convinced that it can't be done, but it's clearly challenging in even the simplest quantum dynamical theories. So I think people have done it for really very simple chaotic systems like logistic maps or unitary maps or something. But for a dynamical system, I'm not aware that even for that kind of thing it has been done.
I see. Okay.
But I mean, I would love to be able to do it. Yes.
Okay. Thank you.
Yeah.
Thanks for the question, Casey. Any other questions? I guess we're running a bit out of time. We can also close the official part. So let me do that and thank Julian again for the talk and for his his answers to the questions. And I'll see you all next week. And I stop the recording.